Hi, this is Rajat Kumar Shukla from Perpetual Learning. Today we will discuss about the half wave rectifier. This half wave rectifier is two types. One is uncontrolled and another one is controlled manner. So what is it and the load, R load, RL load, RLE load, what is the application of it and what average voltage, how we can calculate what average current, what RMS current and what RMS voltage we can calculate it. We will discuss on it. Rectifier basically is used to convert the AC to the DC. Okay, so if you are talking about the DC, so DC may be different kind of available. So kind of suppose one DC is a fluctuating. Okay, so one DC is a fluctuating. So fluctuating, that means it may be this kind of manner or it may be this kind of manner. Okay, so this is kind of DC which is a fluctuating type. Another one is a pure DC. Okay, so another one is a pure DC. So pure DC will look kind of thing, look here. Okay, so here, so the important point is, if you just observe the, if you just calculate the Fourier series, then you will get in the Fourier series there are some harmonics and these harmonics are even harmonics. Okay, so I'm just introducing, there are some kind of DC is available. Input is a AC supply and output is a DC. So usually this is the fluctuating type. Okay, usually this is a fluctuating DC. Okay, so to avoid this fluctuating DC we use filter. Okay, and this filter may be capacitive filter or I can say C filter. This filter may be L filter, this filter may be LC filter, this filter may be LCL, or usually famous name is a pi filter. There are multiple kind of PC filter is available and active filter is also available. But in our syllabus, in the power electronics syllabus, there we will discuss only the C filter and L filter. Only the C filter is enough to be discussed. Okay, and L is obviously will come in the form of L load. Okay, so we will discuss later. So I'm just showing you what is what rectifier will do and what is the objective DC we will get objective DC. Okay, based on the configuration. Okay, configuration, that means if you are talking about the circuit topology, based on the configuration, the first rectifier is a half wave rectifier. Half wave rectifier. Second is a full wave rectifier and third is a full bridge rectifier. Let's say half wave rectifier. Let's say I should suggest name is a FWR for the, which is stand for the full wave rectifier, and this is a full bridge rectifier. Okay, so if I am talking about the half wave rectifier, so here you will use a device, let's say this is a diode and here will be AC signal and here is a load. Okay, this is the load. So if I say this is the diode, so this is, you will say, I mean, if I'm using a diode. Okay, if I'm using a diode, so here you will say this is the uncontrolled type. If I'm using SCR, then you will say this is a control type. However, SCR you cannot be controlled fully. Okay, so suppose that means you can directly turn on the SCR, I mean by applying the gate pulses, but you cannot be turn off the SCR. Okay, for the turn off purpose, there is different kind of commutation is available. For now, we will assume SCR is a half controlled device. Okay, so here this is a half controlled device. Okay, remember the name is should be remember in proper way, otherwise it will confusing in the future terms. Okay, so let me show you, I mean, what kind of load is here in the case of rectifier. So if you are talking about the load, so load first load is R load. Second one is a RL load. Third one is a RE load. Fourth one is a RC load. Okay. However, if you just observe this load, then there are four component, which is R, L, C and battery. Okay, these four component is very useful if you are characterize the load. Okay, so we will start our study of the half wave rectifier using of R load. So as we know, the half wave rectifier circuit diagram is look like AC supplying is here, and here R load is here. Okay, as I discussed, if you are diode, then it you will say this is the uncontrolled kind of rectifier, and if you use the SCR, then this will be controlled kind of rectifier. Okay, so this is a AC supply here. Suppose this is a VAC, and what voltage is here, this is a DC, and what current flowing through it, this is the IDC, and IDC is equal to VDC by R. Okay. So this is a AC signal, this is a peak of the signal, and this is a minus peak of that signal. Okay, so if I am just assuming AC signal, I am just assuming this is a pure sinusoidal sort of signal, and this peak value is a V peak, and this is a sin omega t. Okay, so this is a AC signal with respect to time. So here let's say the diode built-in voltage is equal to 0 here in this case. However, if you are not using the ideal, I mean if you are using the practical or the actual diode, then there are some built-in voltages there. So for the power diode case, it is approximately 1 volt, and for the signal level, for the low power diode, this is the 0.7 volt. Okay, so here what DC voltage is here, so what we will get DC signal, I can say the output voltage in terms of time. Here this is the, if you are saying the positive half cycle, in this first half cycle, what equivalent circuit model you will get, this is the question. Okay, so let's say this is a case where this is a case 1, and again this is a case 2. So case 1 is 0 to pi, and case 2 pi to 2 pi. Okay, so I am just taking this configuration in the case 1. Okay, so diode will turn on because of positive voltage you are applying at this anode. Okay, so in this anode just positive voltage is dropping. So what will happen, diode will act as a short circuit. Okay, and their load resistance R, and the AC supplying is here. Okay, so what voltage across here, what voltage experienced by the resistor is directly directly as a source. Okay, the output voltage configuration is look as a source voltage. So what will happen, the voltage waveform is just like as a input. Okay, in the case 1. In the case 2, negative voltage you are applying. That means if here is a minus, then what will happen, diode will turn off. If diode will turn off, then what will happen, diode is act like as a open circuit. Okay, so what voltage you will what voltage resistor will experience, this is no voltage. Okay, so that means because there are no current is flowing, obviously there are no path to flow the current, then what will happen, zero voltage will be experienced. Okay, so if you see zero voltage if here experiencing, okay, why, because 0 ampere current is flowing through it. Remember, because if there are zero voltage and some current, okay, I'm saying here the voltage VDC is equal to 0 and IDC is equal to 0. So this is the case, load is floating, this is a case of floating. Okay, no connection is there, this is a case of floating. If VDC is equal to 0 volt and IDC is not equal to 0, that means some current is experiencing, this is the case of short circuit. This is a case of short circuit. So remember this condition. This is the very important point here. Zero voltage is experiencing. That means, is it the meaning of the this is the sorted? No, this is not a sorted. Okay, so this is a floating case. I mean case 2. Okay, so what is the current waveform here? Is it as it is same or changed? So according to waveform, it will be same. It will be same, but according to magnitude, it will be changed depending on the what is the resistor. Because I have already mentioned here IDC is equal to VDC by R. So this magnitude, sorry for this drawing, this magnitude peak is depends on the what is the VDC is here and what is the resistance R is here. Okay, and because here is a current is 0, so current will be because diode is open circuit, so current will be 0. Okay, so what average voltage is here? How we will get? Because average voltage somewhere lying, to follow this line here, so this is the average voltage, and similarly some average current is flow here along with time, because this is the average now, because this is the average. Okay, remember this is the average. So to calculate the average voltage here, what you will do, you will just take the instantaneous voltage here. Okay, so you can easily see this is the 0 to pi, and to calculate the average value from 1 upon t, 0 to t. Okay, so because 0 to pi, it is showing some voltage waveform, and this voltage waveform in terms of Vm sine omega t in terms of time. Okay, Vm sine omega t into d omega t, and plus pi to 2 pi, it is 0. So pi to 2 pi, it is 0. So this is 0 and Vm sine omega t. So what will happen? Vm upon pi. Okay, if you solve it, I'm not solving here because otherwise it will take too much time, and this is very simple integration method. Okay, so Vm upon pi. So you will get V naught is equal to Vm upon pi. What about average current? The average current, you can say average value upon what is the resistor is there. So what is the average voltage is there? Vm upon pi into R. This is the average current. Okay, what is the RMS voltage? What is the RMS voltage? RMS voltage is V RMS, output RMS, sorry, is equal to 1 upon 2 pi 0 to pi Vm sine omega t to square d omega t whole root of. Okay, so RMS, that means root mean is square value. So firstly square the instantaneous value, then calculate the mean of that. Okay, and after that square root whole terms, then you will get Vm upon 2. Okay, if you just solving the equation. Okay, now the question is, what about source current? What current is flowing? This is a source here. Okay, so what current is, because current is depends on the load, what is the resistor is there, and what is the current is flowing here, this is the IDC. So obviously if you are talking about the DC current, it is just equal to what is the load current is here, so it is look like same. Okay, so you can see source current is non-sinusoidal. Okay, however applying source voltage is a sinusoidal. Sorry, this is sinusoidal. Similarly, output current is non-sinusoidal and the output voltage is a DC. Sorry. Now here one more question. Suppose if you are applying 230 volt 50 hertz through half wave rectifier, suppose load is a bulb and this bulb is DC kind of bulb. Okay, and this bulb voltage rating mentioned is a 230 volt and resistor is mentioned load voltage is mentioned 230 volt and the power is mentioned 50 watt. Then draw the output current waveform, what current is flowing through it, and calculate what is the watt power it will transfer. Okay, what power it will transfer. Okay, so this is the question. So obviously this is looking because bulb is a resistive load. Okay, similarly if you say heater is also R load, bulb is also a R load. Okay, remember. So to solving this equation, this is a very important point. To solving this equation to problem, what we will do, we can directly draw output when, because we know now this is the R load. So in the R load we know the output current waveform is look like this. Okay, time, and this is the pi, this is the 2 pi. Okay, this is the current waveform for the I naught. So what is the peak value? The peak value we can calculate. How we can calculate the peak value? So peak value is as it is, peak value of the load side is what is the peak value of the source, what is the load resistor R. Okay, suppose this is the equation 1. Okay, suppose this is equation 1. So I need to calculate the R. So before calculate the R, I have to show something about the bulb. Okay, so suppose this is our bulb. Okay, and in the bulb the filament, is look like kind of thing, right? L is very small, okay, or negligible, I can assume, and there are some resistor R. So to calculate the R, I should know I is equal to what is the power rating is here and what is the voltage rating is here. Okay, so I can calculate 230. I can calculate the current. So V is equal to IR. I will use, so R is equal to voltage is 230 volt and what current I have calculated, 50 by 230, right? So this is the resistance R